Thanks a lot, Kadirjan. It was a great presentation, and
Yeah, thank you.
I'm looking forward to assist you. And we are really happy to have Esther as well in the ecosystem right now. She is great, and she will be helping with go-to-market as well. So thanks again, Esther, for helping all the builders.
Thank you, Yasin. Thanks, God. Thanks, everyone.
Hello, everyone. Do you hear me?
Yes, I can hear you.
Awesome. So, yes. So, yeah, I'm presenting now ZK email. I built this project along with Mohammed. Unfortunately, he's not here to present with me, but yeah, I will go through the process. So I would like to give you a small intro about ZK email and why ZK email is important in the world of ZK. So you can have, so emails in general are commonly used on the internet to do a lot of things. And I think anyone who has Gmail can use it in many things, right? So because emails authenticates the user and also has a bunch of information that can be used later. And to give an example, ZK email is also used on Ethereum now for different projects, including ZK peer-to-peer, account recovery via emails, and many other projects. Proof of Twitter, proof of GitHub, proof of Venmo, and those all thanks to ZK email. And why? We can ask the question, why ZK email? And because with the ZK technology, you can have control over which inputs you want to show to the public and which not. So it's like a combination of succinctness and privacy using emails. So, for example, in the context of Venmo or even some group membership, I can, from an email, prove that I'm a member or I did a payment to someone without revealing my email or my identity. So yeah, that's very important. So actually the ZK email in O1JS is heavily based on the existing work on Circom. And I can show you from the graph here that generate circuit inputs is the original one used by ZK email, and we actually wrap that in O1JS. But the rest of the primitives, as you can see here in the graph, are all new primitives in O1JS, and I can walk you through that very soon. So it's fantastic that we built this project in 3 months and actually along ZK regex and O1JS as part of Navigator. It took 4 to 5 months to do everything, including the ZK regex compiler and ZK email. So initially, one second. Yes. So initially, we had 6 milestones, and it was first to research utilities and approach regex and RSA, along with new dynamic SHA-256 base 64 primitives and integration of regex and also adding a functional ZK program. So we delivered the first 4 almost in midpoint milestones. And yeah, I can give recap at the end for that. So our final milestones for ZK regex was to optimize the verifier contract and add more integration tests and publish ZK email. But was a bit abstract, and we did even more in the final milestones. So to give you a quick summary, what we did is a base 64 decode at the beginning, which is inspired from the original ZK email work. And actually, we also added later base 64 encoding because it was a bit more efficient than decoding. And along the way, personally, I had this feeling that since I'm using new primitives in O1JS, I had the commitment to really push PRs to the O1JS repo so other users can use them. And if not PRs, we also published a lot of NPM packages for these primitives. So this one was published as an npm package and then later merged into O1.js. So anyone can use base64 encode or decode as part of the bytes provable class. And we also presented regex and midpoint milestones, but we also integrated this during the final milestones along with something called select subarray. Actually, I can walk you through this, but this is very, very complicated because like it's a way to correctly integrate regex into like ZK. Because I can give you a brief note on that. So regex, following the pattern, filters all of the bytes into zeros and the bytes that following the pattern non-zero. And then you need like a utility function like this one, select subarray, to really fetch the bytes that you need. And this way you really bind regex with the original input. Everything inside the circuit, of course. So we did that in the final milestones as integration. And this one was like the most cumbersome task in the final milestones. And now we have a dynamic and partial SHA-256 primitive in O1.js. Actually, I pushed to PR to expose the low-level primitives of SHA-256, and then I published an npm package for this. And now anyone can use it, of course. And this way you can have, I can walk you through why dynamic and partial SHA-256. Dynamic SHA-256 is like when you want to hash an input dynamically. And how can you do that? Because everything is deterministic in a circuit. So I can hash a circuit that I know is like, I can hash a pre-image that I know is like 32 bytes. But if it's 33, I have to change that. And if I compile that again, I will have a new circuit. So, and this doesn't work for ZK apps or circuits in general. And what dynamic does, it pads up to a constant size pre-image and hashes all of the blocks of that, and then it selects the current block so you can have the correct digest. And this is how dynamic works. And also the adaptation of that is called partial SHA-256, and that also skips the initial. This is a bit complicated, but it skips the initial hash, and then starting from a certain pre-computed hash, you can generate the hash you have. And with this, you can optimize a lot of constraints when using SHA-256. So we also had a new milestone for the project, and we added a lot of benchmarks. I can show you that. We also added a lot of instances of smart contracts that that you can have a glimpse on the rows and why it doesn't work. It can't really generate proofs at the moment. So we added really nice documentation. We published the final project as an npm package. And yeah, I think I can walk you through the README now. So to give you a glimpse on everything is like documented in here, along small motivation, along with like the primitives added to the project. Just a quick reminder, we have a full regex compiler. RSA is now an example in O1.js and also a standalone npm package. This is also part of the ZK email. We did base64 dynamic and partial SHA, and there's also a walkthrough on how to use these as primitives. So as I mentioned before, many applications you can build with this, but the problem is, let me just remove this. The problem is if you want to use ZK email for the moment, it has 340K rows, whereas the limit to generate proofs in O1.js is like 64,000 rows. So it far exceeds that. And this is why, for the moment, it's not usable. And yes, I can show you some benchmarks. In general, like I know benchmarks and circuits, not many people are interested in that, but we also did. I can show you this instead of. Yes, so yes, actually, since we inspired from ZK email and Circom, we have here a table of the primitives and the benchmarks, and you can see here O1.js is very efficient. This is like like it's spectacular in general. And you can see for header hashing, 5 times more efficient, almost like 11 or 12 times more efficient than RSA. The body hashing is like, yeah, again, 4 or 5 times more efficient. Base 64, oh, okay, I think I had a typo here, but it's like okay, 1700, but in Circom is 2000 actually, because it's almost the same. Body hash regex, this looks a lot more efficient, but I also did an adaptation myself on security. So normally it should look like 300K constraints in front of 617, but now it's 86. And after adding the select subarray, it's 145. I know like this looks like, jargon, but this is really, amazing using OpenJS. Yes, so I can show you the graph. Yes. So just a general overview on the architecture of ZK regex. So here in off-chain, we generate the inputs. And I can show you why we do this, actually. So we have this email, okay? So this is how an original raw email looks. And the email has headers, these headers, and have a body. So what ZK email does is that this head, like all of this email is like DKIM verified or authenticated by DKIM signature, and DKIM signature has a lot of metadata about a lot of things. The signature, who sent it, received, the domain, the body also. So this body is hashed, and then base 64 encoded to be found in here, for example. And what we do is we do this DKIM signature in ZK such that we verify that this email is valid. And what we do is we take a signature after sending the email, of course, and we fetch from the DNS registry a public key. And then this header in here is the message to this signature. So we also simulate this in ZK email. And what we do, we hash this, and then we encode this also. We do the PKCS15 encoding so that this is a message for the RSA signature. And as you can see here, it takes 3 inputs: signature, public key, and the message. And why we did dynamic SHA? Because these headers can be different in length. And using dynamic SHA, you can have really a ZK or like a circuit verifier for a certain size of headers, like a certain max limit of headers. And okay, so let's say in ZK email, we verified that this email is valid. But what we did is also is only verifying the headers content, right? So if we stop on that, the utility is really missing. So, and I can prove, so I can show you just a small detail here, is that we return the hash of the public key, because the public key gives information that this email was sent for example, by Gmail. So in a ZK app, you can add that as a public input and assert that, okay, this email was sent by Gmail and is valid. But also, like, if we stop on that doesn't give any information at all, right? So we have to use we have to check the body. And what's the utility of ZK email is that after you validate the body, you can scrape any information from it. So I can fetch this date, for example, or I can fetch Bitcoin. And you can say, like, why do you want to fetch information? Because by the way, I wanted to add this example in Mina. Remember in ZK Ignite, everyone you got funded by ZK Ignite. And I wanted to prove in ZK email that I am a ZK Ignite grantee. And how you can do that is that I verify that this email is sent by Mina. We have that Mina email. And then I scrape certain data from the email to say that I'm granted for that. So with that, actually, you don't need body hash, but you can prove that with body hash, that word, for example, you are granted I can prove that I'm ZK-Ignite grantee. It's less just an abstract example, but it's also possible. So coming back here, so you can see here we have the headers, these headers, and you have also here is called the body, the podded body. So since we give these as two different inputs, what we need to do is to bind the body to the headers. So I can prove that this body is valid along with the DKIM signature of the headers. And how we do that? So I said earlier that the body hash is in here. It's the hash of this, and it's base 64 encoded. This is why we also use the base 64 encoding. So what we do is we take this as a different input, we hash it, we base 64 encode it, and then we assert. So I can show you this. Actually, we did, because the body can have really large size, so we should optimize by two things: the size limit and also partial SHA. Otherwise, we will have millions of constraints. This is why we did partial SHA here. So we did the partial SHA of the body, we did base 64 encode, and then what we did, we fetched this body hash, this one exactly, with the ZK regex. So I can know I fetched this from the headers, and the headers are DKIM verified. So I'm sure the headers is fine. So I just need to make sure that the hash of this is the same as this one. And going back, after using regex, we get the body hash, select subarray, and then we assert equal. And after that, we did what's called ZK email verification. And after that, so this is infra, but if you want to use this in ZK app, you have to scrape certain data from the body, let's say this one, and you have to do also, and scraping data means that you need to use another regex circuit to scrape the data from the body. So for proof of Twitter, they are using a statement called "this email is meant for," and then you scrape the handle. And they are also using a different regex to, for example, in Twitter, to verify that this email came from Twitter. Yeah, so if anyone is interested, I can go into more details in this, but like this is the overview. It's complicated, but it works. The security checks are working. So I can show you also like some challenges that we encountered. Yes. So yeah, so dynamic SHA and partial SHA took a lot of time from me, and I did 3 PRs in O1JS, and those were complicated. But after consulting Grigor, the last one, which is exposing the low-level API, was the one that helped me a lot to publish the NPM package for dynamic and partial SHA. And there was a lot of work when it came to optimization, because I was persistent on making this work on mainnet, but unfortunately it's not possible. And even as you can see that, okay, I showed you here. Let me show you again. So here we have like this one, let's say, okay, let's be pessimistic a bit. So let's say 400K rows, okay? But in Circom, this number is like around 3.5 million constraints. So even so, like after all of the optimization, this is amazing. But unfortunately, it doesn't work. Not doesn't work. You can't really generate proofs with this. So what's happening? Okay. Yeah. So actually, we did this ZK program instances. You can run those. And by the way, like this proves that the code is provable. But when you pass to generating the proofs, you'll have problems. So we'll have ZK program. and these programs show everything. And even this is a good demo on how any dev wants to use the API in general. You can also, I have all of the links, and you can visit you can use all the npm packages and like use the infra in general. I can see someone raised a hand.
There's a question in the chat.
Let me see.
I will read it out
No.
for you. Okay.
No. Because, okay, so that's the detail in O1.js. In O1.js, since like the proofs are generated, I think they were, maybe Gar can like have a say on this. There's an RFC called chunking, and the limit to generate proofs in O1.js is 64,000 rows. It's like 2 to the power 16. And like, I think it's related to the browser and WASM to generate that. And I reached out to the team, and they said, like, with this chunking RFC, they are planning to have this, extended to 2 to the power 17, which is like 120 AK, and maybe in the future 2 to the power 19. So no, Circum doesn't have that problem, and even if you have like 5 or 6 or 7 million constraints, you can generate a proof. But I think the ZK email team did something called ZK chunking and other optimizations to make things faster for them. What I can show you also, like just at the end, so this is called the tester file. You can just give it the path to your email, and I can show you the demo. Please let me know if I'm out of time.
No worries, because the last presentation and we have quite a bit of time, so no worries.
Okay, so I want to prove that I'm honest to you, so I'll show you the email. So this is called the large email file. Now we'll go step by step to prove that to you how things work. So it takes the path. This is a demo on how to use the API in general. And what you do is you take the path of the email file, and then you just read it and give the string to the input generator. Also, this is a helper function for the npm package. What you do only is you give that. Also, like if you are planning to do, so I can show you the types in here. If you are planning to, so the max header length and the remaining body length, these are max sizes set to default. So max header length is 1024, remaining body length is like 1536, and these are values I chose from the main ZK email in Circom. But you have this one weird one, you might ask, is like SHA pre-compute selector, right? And this is a selector to do hash pre-computation. Okay, this is very important, actually. I think it's rare to find an explanation for this, but I can show you. So let's say I'm trying to fetch this hundreds of thousands with regex. And what I do selector is I'm stealing this selector. I only want this one. Okay, so you give it this as a string. And this is an input also to generate for the partial SHA. And how does the partial SHA does? So all of this body in here is pre-computed out of the circuit, okay? So you give this pre-computed hash as an input to the circuit. This is why you have this one. This is why you have, okay, you have it as here. It's called pre-computed hash. So you pre-compute the hash, and then you will only feed this, the rest, even if you have something like this. You will only feed the rest as input to the circuit. So imagine in circuit hashing is only these few bytes. So it's just one block. But the thing is, it's also a bit complicated to explain, but it's also with dynamic hashing is like the upper limit of that with the max size. So you generate the inputs. So I'm not using pre-compute selector. So the pre-computed hash would be the initial one. So, and you have inputs, and you can destruct those in here. And we have a Boolean value. So since this API demo, This one is whether you choose to verify the body or not. And also, this is why we have different benchmarks. Read me. So this is why we have different benchmarks in here. That, okay, no body check. You see, no body check is like 100K rows, but with body check is like 340 and 386. So you have the option to do that. So it's flexibility in the API. It's also like by ZK email. Okay, going back to the code. So yeah, you destruct the inputs here, and then you can verify the email simply with this API. And this API, as you can see here, I have promise word. Okay, I have the hash email verify, and yeah, so yes, so it returns the public key hash. Okay, going back to the tester. So let's run this code and prove you that this code really verify emails in general. So if I do npm run tester, so nothing happens. That means it's fine. It works well. So if I do false and I do npm, then it should work also. So it worked. So that's true. Imagine why ZK email is very interesting is that, let me change the first input. The input, this one is the headers. So imagine what I'm doing here. I'm just adding a 0 byte to the headers. And since we are hashing, let's see if this works. Because we did many security checks for ZK email to make sure that nothing is wrong with that. So it's not only infrastructure, it's also like with a lot of security checks. So if we do the tester again, you see it fails. It's just like it's a simple 0 byte. And I can take this and I can do that for the body also. And if we do that, npm run tester, it fails. But what if we skip the body check? I think everyone should agree that it should work. Right? So it works. So any of these inputs, there's a lot of security checks in here that if you tamper with any one of these, you will have an error. And also, like, since some of the O1.js API doesn't really return error messages, so if you go to .test email verify, you will also have some comments in here. So it's without specific message, you will have what the message should look like. So for example, this error looks like this. It's ugly, right? But at least in the tests, I made sure to deliver that this is because of header hash index. In general, like an error like this is because of RSA failure. And RSA failure is for many other reasons. So the documentation doesn't stop on the README. So feel free to go through the code, the tests, the tester, the function. This also contains benchmarks, also some mechanics of ZK email. Feel free to navigate through the NPM packages. And I think, I hope that it's beneficial for other devs on Mina. I think this is my presentation. Thank you.
Hi, Yasin. Yes. Well done, Mahmoud. Thank you for that wonderful presentation. We're very detailed. I think that was the first thing I noticed. Yeah, it was really,
Sorry. Yeah, it's ZK email at the end. Yeah.
and your documentation as well. So I'll just let Yasin speak now.
So I have, I guess, two questions to start. Like, one to start with is, so as we are all familiar with, ZK email is probably the most famous use case in the zero knowledge industry in general nowadays. So that's comes with the question of how you compare like ZK email in O1.js and on Mina protocol in comparison to Circom and the Ethereum world. So how would you compare it, and like what are the advantages of doing it in O1.js, or maybe from the user's perspective as well? But that's my first question. Yeah.
Yes. So building this in O1.js is really interesting because first, as I explained earlier, like it's way more efficient than other circuits in Circom. So this is like, I think it's like, yeah, nine or 10 times more efficient than, at least in constraints, because you can't really compare those one to one. But it's very efficient in constraints compared to Circom. This is one. And anyone can really say this if they use SHA-256 or any other primitives or range checks. So this is really special to O1JS. And the second thing is that even the ZK email team built many primitives themselves. They audited many primitives because if you are familiar with coding in Circom, it's really difficult to find some implementations here and there. And even if you want to go through one yourself, it's really difficult. Like Circom DevX is terrible. So what made life easier for me in O1JS is that it's like it has many primitives, many optimizations. RSA was almost ready. There was a small fix. I fixed that, and Gregor pushed the example, and I exported it as a package. Gregor assisted me a lot. Like it was really nice experience to do PRs, to merge PRs, and to publish NPM packages for this. So I think to emphasize on this, if you want to really build ZK email with other ZK DSL, it would be like really, really difficult to do that. Is that okay? So Mario, you said, can you repeat the GitHub repo info? Which one do you mean?
I think the GitHub overall, maybe. I think maybe.
Ah, yeah, I can send that. Yeah, sure.
Sorry, I have two more questions. So
yeah, go ahead, please.
The next one is I think you already talked about it, but like so what are the main blockers right now to take ZK email live? And like, is there any work streams right now in O1 Labs targeting this blockers? Because this is a really important use case, and I am receiving lots of messages and interest from external ecosystem players and even ventures as well. So it's just, I'm curious if did you communicate these blockers with O1 Labs, and if there's initiative targeting these blockers that you face right now to take it mainly.
Interesting. So the blocker is this limiting constraint. So even, by the way, this is email verification constraints. It's like 340K rows. But even if you have a ZK app, then you would add 2 regex circuits. And I think that will add the total constraints like 700K or something. So 700K compared to 64K is really large. And I think, okay, so this is just like speaking the way it is, because this is just built in 3 months or 4 months. So like speaking with the O1 Labs team, they said like this chunking implementation can really raise the constraints. That's really good if that happens soon. And other things like if we work on ZK email to optimize, then we can have some hope to launch this on mainnet. And how can that go? Let me explain, for example. So yes, have this one. Yeah, so so for example, like we have the body hash check, as I showed you here. Like it's a one that you can control in here. So what I was thinking also with Mohammed is that composability of proofs is that in a ZK app, instead of doing this all in one proof, is that you have DKIM verification with public output input as the headers, and you feed that in another proof for the body check. So if we have body check verified in a circuit for that purpose, then that would work, because we just pushed some we could use that with ZK program. And this way we lifted all of this. So for example, if we do that efficiently, and just like making some speculations here, is that instead of 386 or 340, we could just add a bit from here, because we are just doing some proof verification. So with proof composability, and that's also special to O1JS, we can do that in ZK apps. And also, like, to add on that, some optimizations with ZK regex and some utility functions. So yeah, so this utility function, the whole regex takes 86K here, but selecting the subarray is 60K. This is a lot. Even I consulted Greg around this, but I just used the same complicated implementation as in Circom, and it was, I just tried to make it work because it was too much. But yeah, this could be optimized. This is what I wanted to say.
All right. Okay, thanks. And promise you this is my final question. So as working closely with the grant programs and all the developers and entrepreneurs in the ecosystem, I think this is really important because it widens the things that you can use ZK email and like build on top of it, such as, which is another very famous and product in privacy scanning exploration, like ZK P2P. So like, do you think it's possible right now to like work on a proof of concept, like building a peer-to-peer payment system using ZK email? Do you think it's feasible? Or that's my question.
I think it would be painfully feasible, maybe. So these three words. So you have to painfully work on that, painfully like optimize and like refine a lot of code. So with like other architecture for like composable proofs and many other like techniques. So because like we are looking at just email verification, because you have to add a lot of other things if you need a real application. So yeah, I think with a lot of work, maybe it's possible in the future, but I can't really say in the near future.
Okay. Sure. Yeah. Thanks again. And sorry I bothered you with questions. And
No, please go ahead if you have any more.
This project is literally, one of my top projects in the ZK space. So I am keen to see support and see you going forward. Yeah.
I'm happy to know that. Thank you, Yasin.
Thanks.
Okay, thank you. I think that's the end.
Thanks, everyone. I think it's the end of it. Yeah.
Yeah. Okay. Bye. I'm going to stop recording now.
Thanks, everyone.